My name is Hanuka, and I'm a research scientist at Slack. And actually, this image right here was taken a little over 2 weeks ago, where the upgrade of LCLS just produced a light for the first time since it was upgraded. Why do we need to do online tuning and control of particle accelerators? So usually those accelerators are very big devices, and they have hundreds of knobs that could be tuned to produce those X-rays with specific properties. And typically we spend over 500 hours per year in hand tuning. So this is a lot of time spent on tuning, and we could actually fit many more experiments rather than spending those on tuning. So our goal here is to expedite particle accelerator optimization and maximize the control and tuning by developing algorithms that can learn like living beings. And when I talk about learning like living beings, I talk about Bayesian optimization. So why did we choose Bayesian methods? On the one hand, we have the human optimization, that we are lifelong learning. We learn from experience, but sometimes we suffer from mental modes and we make relatively slow decisions. On the other side, we have numerical optimization, where those could learn in bulks of data and juggle many things at once and make fast decisions. So by combining the strengths of human optimization and numerical optimization, we introduced the model-based Bayesian optimizers. And the reason that we use model-based is because a good regulator of the system is a good model of that system. So let's have a quick refresher about Bayesian optimization. We have some unknown objective function, and we want to find its maximum. So we build a type of probabilistic model, kind of a surrogate model. In this case, we chose Gaussian process. You can see here the mean of the Gaussian process and the uncertainty. Then we take a sample from the machine. In our case, it will be a quadrupole and the corresponding FEL energy. Here it is. I just sample the point. So then I update my surrogate model. Then I need to choose the next point to simultaneously increase the objective and decrease the model uncertainty. And this is done by maximizing an acquisition function. In our studies, we used upper confidence bound, which is just the mean of the surrogate model plus some sigma. So the acquisition function suggests the next point, and then we sample the new point on the machine, and we do this iteratively until we reach some computational budget, or we are happy with the maximum. So it's going to look like this, and then we're going to sample this point right here, and so on and so forth. So if we were to look at this as a continuous process, we just keep sampling from the machine, and the Bayesian optimizer suggests to us the next set of controls we should put on the machine in order to evaluate the FEL energy. So I mentioned that we used a surrogate model, and the surrogate model we used is a Gaussian process, which is just normal distributions over functions. A nice property of the Gaussian process is this kernel, which is actually interpretable, and it encodes the smoothness between two adjacent points. We like Gaussian processes because it gives us a reliable estimate of the uncertainty. We could also use Bayesian neural network, for example, here. So, and the kernels shape our belief of the system. So for example, if we were to use a radial basis function, then which looks like this, radial basis function kernel, which looks like this, then you see that the Gaussian process is smooth. And if we were to use exponential kernel, you can see that it's more jaggy. And last thing that the reason that we like about Gaussian process is that even if the optimum jitters day to day, we don't care about the mean. We care about the fact that the kernel captures the shape. So as long as the shape remains more or less the same, even if the mean changes from day to day, then GP is still a good fit. So we have this kernel. Here is the form of the radial basis function kernel that we used. It has its hyperparameters, amplitude, precision matrix, and noise. So now we need to determine those hyperparameters. So traditionally, it is done by maximizing the marginal likelihood of a given data. So you can see here how we do that. We just for each quad or for each input control, we scan the length scales, and then we record the likelihood, and we choose the point which maximizes this likelihood. So this precision matrix is just a diagonal matrix, as you see here, and each element on its diagonal is determined from this process. So then how do we use this to automate operations? We want to optimize the free electron laser energy with respect to 12 quadruples shown here. And we build our probabilistic model with GP, we choose kernel, we tune the hyperparameters, and then we use a framework developed in collaboration with Daisy. This is just a GUI that controls batches of devices and connects between the machine interface and the algorithm API. So with this, we applied it on the LCLS, and you can see that our GP reached a higher optimum of X-ray pulse energy, and it did it 4 times faster compared to traditional simplex algorithm that was used. Okay, so that's a nice first speed up, but the question is, can we speed it up even more? So the answer is yes, if we were to use correlations in the kernel. So, you know, the FEL energy has the input controls has correlations where they produce the FEL energy. But if we use isotropic kernel, meaning only diagonal kernel, we can do just as fast as, you know, as I showed you. But if we were to use correlated kernel, which captures roughly the relative relations between the input controls, we can perform much faster. And here you can see that it actually becoming more and more enhanced as the input dimensionality grows. We call this approach semi-physics informed because the correlations, we could not establish those from data. You can see here a bunch of scans, and there is no clear correlation. We plotted here the correlation coefficient between 2 adjacent quads that typically should be anti-correlated to each other, as shown here from simulation. But due to the sparsity of the data, we could not resolve those using the traditional method. So we went ahead and we calculated the correlation from a simulation model, from a physics model, and then we incorporated those into the kernel matrix. And you see here that we were able to gain a little bit more speed up and better performance. This is on 4 quads. So the dimensionality is less. So again, it will be enhanced as the input dimensionality will increase. Okay, so this is very convoluted process to calculate this to calculate the diagonal from data, the off diagonal from physics model, then combine those. So here we present a full physics informed kernel. And the reason that it is cool is because you can actually tune the kernel hyperparameters without any archive data. So our goal is actually to calculate the kernel directly from physics model. And in order to do that, we view the kernel as a convolution of basis function, which each basis function is being approximated with a simulation or analytical model. Just to give you an example, if we have Gaussian basis function right here, then the resulting kernel function is the RBF, where the precision matrix is half of that basis function. So with this in mind, we went and applied it to our simulator. We know roughly where is the peak of our simulation. And then we did a Taylor expansion to second order in log space in order to get Gaussian basis function, as I show here. We perform this autocorrelation, and we get the RBF kernel. And you can see that in this case, the precision matrix of the kernel is a full matrix rather than just a diagonal. And it's pretty straightforward and easy calculation to establish the full matrix. So this kernel was trained on simulation. Now I'll show you in how it performed on the machine. So it's kind of a kernel transfer learning, if you'd like. So we demonstrated on spirit tree storage ring, which has 13 quadrupoles around it, and we want to maximize the beam loss rate with respect to 13 skew quadrupole magnets. So here you can see two comparisons, one online on the machine, one in simulation. The Gaussian process with the full physics kernel is shown here in blue. It is much faster than other traditional methods like RCDS and simplex used. And it is a little bit faster and find a little bit higher optimum than the diagonal kernel, which was used traditional method of training the hyperparameters. So just to summarize, we saw today Bayesian optimization with Gaussian processes as surrogate to tune a linear accelerator and a storage ring by maximizing 1D objective using tens of controls. We saw the transfer kernel learning, physics-informed GP, where we used a physics model to inform the kernel selection rather than using maximization of the likelihood on archive data. And we saw the basis function kernel as a convenient method to the alternative method using data. So just the takeaway that I'd like you to remember from this quick talk is that a physics-informed basis function kernel could be used to tune new machines without any archive data. And thanks all.
Thank you. Thanks. Very interesting topic. Not something that we discuss very often. So let's see if we have any questions.
Yeah, we don't have any questions right now. We do have a little bit of time before the break if somebody wants to add one.
So if I may, to make sure I understand exactly what's being talked here, because I'm pretty unfamiliar with this. In experiments that we're dealing with, it's very important for us to maintain and control in real time some parameters of our mostly cryogenic detectors, so they don't explode basically. In that sense, it's a task that's maybe somewhat similar when it looks like you have to have an online control of different beam parameters, right? Mm-hmm. And we use those PID algorithms that try and maintain the important parameters in the correct ranges. Is that something that you could also potentially do with this type of Bayesian optimization? Take a parameter like a temperature of the detector and tie it to other input parameters, like supply of xenon, and make sure that it stays and reacts very fast to all changes.
Yeah, so so it depends how fast you need it. For now, for the code that we have here, each acquisition takes around 1 to 2 seconds. So if you need to stabilize something faster than that, so you're limited to the calculation time of the acquisition. I think that for stabilizing PIDs, there are like other methods that probably would be more you know, more straightforward, like feed-forward neural network for control, kind of a lookup table. And yeah, so I think for that application, probably there are other methods that would be better.
So we'll skip to pages. Was there any other comments from somebody?
No, nobody has posted any questions yet.
Well, let's thank the speaker